Howdy, howdy, this is Mr. Potter. Today we're going to be talking about power functions and polynomial functions. So this is going to expand a little bit about what we talked about with quadratic functions before. So I want to start off by introducing the idea of a power function. So a power function is a function that can be expressed in the form f of x equals k times x to the p power, where k and p are real numbers. So there is anything that I can represent with some number times x raised to some power, that's going to give me a power function. So k is the coefficient, and p is the power. So if I was to write a function like f of x equals 3x to the fifth, that would be an example of a power function. I could have g of x being equal to 6x to the negative 2, or h of x equals 1/2 x to the 1/3, and those would also be examples of power functions. I could even have j of x is equal to 4, because this is really 4 times x to the 0 power, and it's perfectly acceptable to have a 0 as an exponent. All of these are examples of power functions. I can put any number I want in front, so I could even have something like k of x being equal to 17.3 times x to the pi power. As long as I'm using a real number for the coefficient and a real number for the power, then I'm writing a power function. Now, this is interesting because almost all of the parent functions that we've talked about so far are examples of power functions. So when I talk about the constant function, then I'm talking about something where the power is 0. When I talk about the linear function, then I'm talking about a function where the power is 1. My quadratic, that's an example where my power is 2. A cubic is where my power is 3. But even some of the other functions we talked about, so for example, our reciprocal function was where my power equals -1. And of course, our reciprocal square is where p equals -2. And our radical function, so our square root, that's where p equals 1/2. And our cube root is where p equals 1/3. All of these are examples of power functions. So these are a lot of the parent functions that we've been dealing with throughout our course. All of them are examples of power functions. So once I have a particular power function, it's often helpful to talk about the end function behavior, because I notice that when p equals 1, or when p equals 3, or when p equals 1/3, or when p equals -1, I notice something about my functions. I notice that all of my functions have some business going on here at the origin. Either I've got a root here or I've got asymptotes here, and I know that my function tends to go off to infinity as x increases without bound. I know that my function tends to go to -infinity as my x value decreases without bounds, because I notice that whenever I have my linear function, or whenever I have my cubic function, or whenever I have my cube root function, or whenever I have my reciprocal function. Well, my reciprocal function is a little bit different. It's actually going to 0 instead of infinity, but that's because x is really in the denominator. My denominator is what's really getting bigger and bigger. And I also notice that when I'm talking about my even functions, I start noticing that as well. So when p equals 2, I start noticing that I've got this other behavior like this. Of course, my parabola behavior, the stuff goes off like this. Similar thing happens if I was dealing with something to the 4th power. Let me draw that a little bit better. 4th power should be a power. I'll notice that it starts being flatter here, and it gets steeper up here. It should be steeper. Let me try drawing that again. It should be really steep. And so what I notice is that if p is even, then I'm going to see behavior where it's going up and up. Or I'll see behavior where it's looking like this, down and down. This is, of course, what's going to happen when k is negative. If k is positive, like in all of our parent functions, k is 1. If k is positive, then I'm going to see up-up behavior. And if k is negative, then I'm going to see that down-down behavior. But if p is odd, then what I notice is I notice this down-up behavior. And of course, stuff's going to happen in the middle, and that's perfectly acceptable. This, of course, is what happens when k is positive. I'm going to see the reverse of that. I'm going to see up-down behavior when k is negative. Now, if I wanted to, I could picture what's happening here by substituting x equals 1,000. Because if I want to know what's going to happen for a function like f of x equals x cubed, well, if I take a look at 1,000 cubed, well, that's going to be 1,000 and then 3 more zeros and then 3 more zeros. So in other words, 1 billion. And of course, this is positive, so this is really shooting up into the stratosphere. And if I look to see what happens when x equals negative 1,000, if I take a look at negative 1,000 cubed, then of course, negative cubed is negative times negative times negative, so my result's going to be negative. And it's going to be 1,000 times 1,000 times 1,000, so it's going to be really going down. So I notice that for large x values in magnitude, if it's positive, it's going up. If it's negative, it's going down. That's for odd powers. But if I was going to do the exact same thing for g of x equals x to the 4th, then if I looked at 1,000 and raised that to the 4th, that would be 1,000, 000, so again going up. But even if I looked at a negative 1,000 to the 4th power, well, a negative to the 4th power is negative times negative times negative times negative, so I'm going to have a positive here, and it's going to be a positive trillion. So again, going up. So I notice that these even ones are going to have this up-up behavior or down-down behavior if there was a negative in front of this. Similarly, my odd functions are going to have the up-down behavior or the down-up behavior depending on the coefficient, depending on the sign in front. So we'll often be talking about end function behavior because it'll help me to do a rough sketch of my graph later on. And of course, we're familiar with parabolas having this type of behavior. If my lead coefficient a is positive, then my parabola opens upwards. If my lead coefficient a is negative, then my parabola would open downwards. So if I continue this, I want to talk a little bit about what a monomial is and what a polynomial is. So a monomial is a power function where p is a non-negative integer. So in other words, it's not going to be one of these situations where I've got a fractional power or where I have a negative power or have an irrational power. It's just going to be a positive or 0 integer. So I can have something like x to the 0, x to the 1st, x to the 3rd, x to the 349th. As long as this is a non-negative integer, these are all examples of monomials. Mono, of course, being 1. So I'm really talking about a single term. Of course, we've seen with our quadratics and with some of our other polynomials, polynomials are made up of one or more of these monomials. So a polynomial is a linear combination of one or more monomials. Now, when I say linear combination, I mean I'm taking one plus another minus another, some adding or subtracting a whole string of these. And I have to have at least one monomial for this to be a polynomial, but keep in mind that my coefficient can be equal to 0. That's perfectly acceptable. My coefficient can be negative, my coefficient can be a decimal, or it can be a fraction, or it can be a square root, or it can be any other irrational. My coefficient can be any of these things. The only restriction is that my power has to be an integer that's greater than or equal to 0. So when we're talking about monomials, when we're talking about polynomials, we'll often talk about the degree of a polynomial, and we'll also talk about the leading coefficient of a polynomial. So when I talk about the degree of a polynomial, the degree of a polynomial is the largest power in the polynomial. So when I talk about the degree of a polynomial, I could talk about something like f of x equals x to the fourth minus x to the fifth. My degree is 5 because that's the largest power that we see here. If I have something like g of x equals 3x cubed plus 6x to the sixth minus 4x to the fifth, I would say that this has a degree of 6. So the degree is really going to have to deal with whatever my largest power is in my polynomial. And my leading coefficient is the coefficient of the term with the largest power. Now we're used to seeing it in the first position, but here my leading coefficient is -1 because that's really the coefficient that I have in front of x to the fifth. Here, my leading coefficient is 6 because that's what I have in front of my x to the sixth. And so what's important to remember is that the degree and the coefficient, the leading coefficient, are actually going to determine the end function behavior. My end function behavior of a polynomial is the same as the end function behavior of the largest power and lead coefficient. So in other words, if my degree is 5 and my lead coefficient is 1, I notice that this is odd, and I know that this is negative. So because this is odd, I know that I'm going to have the alternating behavior, and because this is negative, this is going to be something that's going to go up, down. Now, of course, what happens in between, I could have any number of waves or whatever, and we'll talk about that in a few minutes. Here, my degree is 6, so it's going to be an even function. My lead coefficient is 6. So because this is even and this is positive, my end function behavior is going to be up and up. And of course, things are going to happen in between. I could have waves, I could have humps, any of that can happen. But whatever that dominant term is, the one with the largest power, that's going to determine my end function behavior for the entire polynomial. Because if I have 1,000 raised to the fifth power, this is going to dominate 1,000 raised to the fourth power. In other words, any value that I get from this term is going to more than overwhelm any value that I get from this term. Any value that I get from this term is going to more than overwhelm any values that I get from those terms. So the highest degree and the coefficient of that highest degree term, that's really going to determine my end function behavior. Now, we've already talked about a lot of the properties of these functions. We've talked about x-intercepts and we've talked about y-intercepts, but something else that I would like to talk about is the zero product property. The idea is that if I have two functions that multiply to give me 0, then either one of those functions is equal to 0 or the other function equals 0. This is always going to be true, and we saw this back in Algebra 1. If I had a polynomial like x squared plus 5x plus 6, and I knew that that was equal to 0, I knew that if I could factor it, then either one of those factors had to be 0 or the other factor had to be equal to 0. And this is going to be true if ever I can factor a polynomial, then these factors are going to help me find my solutions, my roots, my x-intercepts. And it's going to be important because sometimes they're going to occur more than once. Because if I'm talking about the multiplicity of a root, I'm talking about how often that root is a solution. So if I was to have something like x plus 2 cubed times x plus 3 to the 5th, then I'm still only going to have two solutions. My solutions are going to be exactly the same as I had over here. But negative 2 has multiplicity 3, and negative 3 has multiplicity 5. And it's important to understand that because keep in mind that if I was to multiply this out, I'd have x to the 8th plus da 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 da. No idea what these other terms are. But really, this term is the important term because it determines my end function behavior. But I know that an 8th degree polynomial should have up to 8 solutions. 3 of them just happen to be this value, and 5 of them just happen to be this value. And so this idea of multiplicity really helps me to understand how my function actually behaves. So if I want to talk about the graph of a function like this, I need to know, is my graph actually bouncing off of the x-axis or if it's passing through the x-axis? Because having a solution just means that the value happens to be on the x-axis at that point. I could have a function that bounces, or I could have a function that actually passes through. And how do we determine that? That's actually determined through the multiplicity. In other words, if the multiplicity is even, then the function bounces off the x-axis. But if the multiplicity is odd, then the function passes through the x-axis at that point. It's really important to note that these both happen at that point. So I want to go through an example of this. I want to talk about what's going to happen here. So let's do an example of this. So let's say that f of x is equal to this polynomial, x minus 3 squared times x minus 1 cubed times x plus 4 squared times x. Now I'm looking at this polynomial and I'm noticing that x equals 3 is a solution. This term tells me that x equals 3 is a solution. And we have a multiplicity of 2 on that because it's this term squared. X equals 1 has multiplicity 3. X equals negative 4 has multiplicity 2. And x equals 0 has multiplicity 1, because this term really has a 1 exponent on it. And the degree of this polynomial is also 8, because if I was to multiply this out, I'd have x squared, so that's a total of x cubed. 3 more makes it x to the 6th. 2 more makes this x to the 8th. So I'm really dealing with 1 x to the 8th. So my end function behavior is up, up. But what's actually happening, if I was to actually try and plot a graph of this, is I know that I have a solution at 1 and at 3 and at negative 4 and at 0. But I know that this is supposed to go up. And I know that at x equals negative 4, we have negative 2, so this is a bounce. So that means that my graph is really going to go down to here and bounce up. I know at x equals 0, I have multiplicity of 1. Since it's odd, we're going to pass through. So this graph is going to pass through the x-axis here. X equals 1 has multiplicity of 3, so this is another pass through. So this is going to go up through like this. And then x equals 3 has multiplicity of 2, so this is another bounce. So this is going to bounce here at 3. At 3, my goodness, that would be really nice if I actually put that at the correct point. Bounce at 3. Notice that I still have this up behavior. My graph increases as x increases and decreases without bound. I have the solutions at x equals -4, x equals 0, x equals 1, and x equals 3. But I've got this behavior where occasionally it's passing through if this number is odd, and then it bounces off the x-axis if this number happens to be even. So I get a pretty good idea of what my graph looks like based off the multiplicity of each of these roots. Last thing that I want to talk about, though, is how do I know how many roots I could have, the number of roots or the number of extrema, the number of ups and downs, humps, if you will, a polynomial will have. So keep in mind that a function of degree p will have at most p roots and p minus 1 extrema. In other words, if I'm dealing with x squared, I know what the parent function for x squared looks like. I end up having at most 2 solutions. This is an example of where I have 1 solution. But of course, if my parabola passes through the x-axis, I can have 2 solutions. But if I have x squared, if I have a parabola, there's no way that a parabola can actually cross this line more than 2 times. If I'm crossing more than 2 times, I'm really more like a cubic. And similarly, I'm going to have 2 minus 1, or 1 extrema, 1 low point, or a parabola would have 1 high point. I'm always going to have the same number of solutions as the power, and I'm always going to have 1 less maximum or minimum. If I'm dealing with a cubic, I know what my parent function looks like. My parent function has this behavior, but I know that if I do transformations on it, I can actually end up with a cubic that kind of passes through and passes through like that. Or I could have a cubic that does kind of a bounce if I had multiplicity of 2. But the thing is, I can't cross this line more than 3 times. I can't take a cubic graph and go, huh, 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 huh. Because as soon as I cross it more than 3 times, I no longer have that third power. It looks more like a quartic, or it looks more like a quintic, or it looks more like a really large power. Similarly, I'm going to have at most 2 humps. So here I had no humps. Here I had 1 hump, 2 humps. Here I have 2 humps. I'm always going to have no more than 2 humps for a cubic. I'm going to have no more than 1 extrema, 1 max, or 1 min for a quadratic. If I was dealing with a 5th power, I could have no more than 4 humps because I have 5 possible solutions. So the degree that we're dealing with is going to determine how many roots we could possibly have. And of course, we could have fewer roots. If I take a look at this cubic, or this quadratic, excuse me, this x squared, my parabola could be completely above or completely below the x-axis, in which case I have no solutions. I could have no solutions, I could have 1 solution, I could have 2 solutions. If I'm dealing with a cubic, because of the end function behavior, I have to have at least 1. That's going to be true for any odd. Because of this idea that I've got down-up behavior or up-down behavior, it's going to have to pass the x-axis at least once. If I have an even power, I could possibly have none. Because of the up-up nature or the down-down nature, I could possibly have no solutions because I could stay completely above the x-axis or completely below the x-axis. Understanding all of these properties really help us make the connection between the algebra, the function that we see written in algebraic form with powers and coefficients, and the graph, which helps us to visualize what's going on with solutions and increasing and decreasing and maximums and minimums. We really need these connections between polynomials in an algebraic sense and polynomials in a geometric sense. Once again, this is Mr. Potter. Thank you for watching. Have a great day.